G'day, my name's Steve and this is Reevesy's Workshops. Today we're going to carry on with part 6 of building the Garratt. More work on the front tank to complete those winglets. Then I'll go on to complete other parts of the 2 tanks and do a bit of finishing touches. Now that I've got the wings fitting properly, they look pretty plain compared to what you see along here. So what I'm going to do, as well as these front ones which hold this in place, I'm also going to put a row along here and a row up the top here. They're all dummy, but it just adds to what you see here and take some of the plainness out of it. So I've got one of them set up in the milling machine here, and you can see my setup. You can see on top here I've actually spotted the holes to do the top. I need a jig of some kind to line all the holes up. You can see them on the side here already done. And it just so happens this piece here was a piece that the sheet metal worker folded in the wrong place. So he made me a replacement one. And it had holes in it already done by the laser cutters before the bending process. So what I've been able to do is use that as a jig to drill the holes. So at first I had it clamped on the side here, held it in my drill press and drilled those holes through, and they were clearance holes. And then what I've just completed was I had it bolted on the top here and spotted through with the drill. Now I've got the tapping drill in, and I'll pick up on all the spot marks using my digital readout. Now I can drill and tap as I did before. So here's one of the little winglets all finished, and I think you'd agree with me it looks pretty good with these extra rows of screws, which are really dummies, and then the one on the front that's holding everything together, and it's really brought some colour up on the panel and taken some of the plainness away. Next thing I'm going to do is to cut out the holes for the lubricator pockets so you can get your hand in and fill the lubricator with oil. So I've stripped the tanks down, both of them, just left the plate where the hole is going to go in it, and blackened it here with felt pen so I can scribe the holes, the lines for the holes. You'll notice this is a little bit of an unusual scriber I've got here. This is made of tungsten steel that's been specially ground down for me by a friend, and it's really hard and it's never worn out on me. It's fantastic. Here's the side of the other tank, and what I'm going to do is I'm going to chain drill out the hole, and the easiest way to do that is to transpose the lines on the inside to the outside. So I've used this hole as a reference point, very carefully marked out where the first line's going to be. Use the engineer's square and a scriber and scribe the lines out, once again using the black felt pen to make the lines stand out. And now I can chain drill from this side. To do the chain drilling, I've grabbed an old drill that's broken long ago and resharpened it up again, and you can see it's a process where you drill holes close to one another, and you need to be careful that you don't drill too close to the line If you can even get the drill holes to touch one another, that's great as well. And then I will break this off, as I'll show you when I complete this. I've got the plate sitting on the drill press. I've got a piece of timber underneath to stop the drill damaging the table, and I've kept the angles in here to keep everything square. I've got spaces under there to hold everything level. So now we'll continue on with the process. I've now used the Dremel with the cutting wheel on it to cut between the holes, and this should now just pop out. Next step is to clean up the edges with the 4-inch angle grinder that you can see in the background there, and then I'll finish it all off with a file, make it look nice. Here's the cutout, newly filed up. I haven't shown you the filing process because you've seen it all before, but it looks all pretty neat. I can get my hand in and get at the lubricator. So I've partly dismantled the tank again, as this cover has to be welded in place. So I put a whole lot of instructions on there, and now I'm ready to take it up and get welded. While I'm waiting for the time to go and see the welder to weld up the tanks, I'm going to catch up on some odd jobs that I have to do. And one thing that happened to me recently was when I was air testing one of the engine units, I found this boss starting to come loose. This has been silver soldered on to the crosshead, but what's happened is I haven't used enough silver solder. I've tried to make it look pretty, and in the process the joint's too weak and starting to fail. So I've fixed this one, and I've fixed the one on the other side. So now I'm going to go to the other engine unit and fix that. So I've pulled the crosshead apart, and this is the inner parts of it here. And just if we have a look through the magnifying glass here, you can see where the silver solder's been around here. And yes, it looks nice and pretty, but it's just not strong enough to do the job. So I'm going to add some more to it and strengthen that joint up. So the next step is to get the body all nice and clean, because you get oil and stuff all trapped in here. So I started by using a white cloth, white because it's got no dye colouring in it. Soak that in acetone and clean it all off. But then I've decided to give it a pickle to make sure we've got rid of everything. Now in the old days, pickle barbs were made of sulfuric acid, and this is an old bottle, as you can see, that I have. And what you used to do is you used to mix 10% of this with water, and that would give you your pickling solution, and you'll see that in the old model engineering journals. However, as you can imagine, these days it's seen as a rather delicate liquid to use, and it's hard to get, because when I first started, the lead acid battery, the battery you'd use in your car, had a liquid inside it that held the charge, and you had to maintain a certain SG level, specific gravity level, so the battery wouldn't go flat. And this was used for keeping that SG level correct. Well, today battery technology has improved quite a lot. For instance, you can use gel batteries and maintenance-free batteries, and this has all become redundant, so it's hard to get hold of. So what we tend to do these days is to use a citric acid bath instead, lemon juice. Now I like to mix this one up a little bit stronger solution than the sulfuric acid, because it tends to be not quite as strong. Takes a little bit longer to use, but it works. It can be bought in the supermarket, and when it's spent, it's biodegradable, which means you can drain it away without hurting the environment. So the crosshead then was put in that solution for about an hour, and now it's pretty clean, so I'm going to set it up to solder before it starts to oxidize. As I'm brazing small components, I only need a small amount of my pickle bath. So the front container here is the citric acid one, and you can see it's worked. There's a bit of dirt floating around on the top there. The one behind it's water to flush everything clean and remove any residue. Then I've grabbed my flux, Easy Flow number 2, painted it on the crossheads, and now we can place the silver solder on it. The silver solder I'm using is 45%, and you can see I've cut it into tiny little pieces. Use the side cutters to show you just how small they are. So what I'll do now is put them on the crossheads. They'll probably disappear in the flux, but I'll show you where I'm going to put it. As I suspected, they've disappeared into the flux, so you can't actually see them, but I've put them in here. So the next stage is I'm going to warm up the body of the crosshead very carefully, and then I'm going to allow the heat from this to actually melt the little piece of silver solder there and fill in that joint with capillary attraction. I'm not going to show you the process here because the camera doesn't have a zoom lens on it, and I'm worried about the heat attacking it and damaging it, so I'm going to do it off camera. But basically I'm just going to heat this area up very carefully, and then this, and gradually bring it up, and it'll go a dull red colour. The flux itself will turn into a clear liquid, and it's at that point the silver solder will start to melt and run around the gaps here, adding to the existing silver solder and doubling the strength of the joint. Once done, I'll come back again and show you the end result. So you can see that the crossheads have now gone a dull black colour because of the heat, but you can also see I've doubled the amount of silver solder on the joints now. So I had to get it slightly hotter than the dull red, as I had to reheat the solder that was already there as well. But it looks like it's flowed nicely, so we'll clean it up now and double check it. Now when we have a look at the silver solder, we can see we've got twice as much in there as we had before. It's giving me a nice fillet. I turn it over and you can see there's a nice fillet there as well, gone all the way around, so I'm happy with that. So we'll clean it back to its nice polished form and put it all back together. The crossheads are now reassembled, and I put all the motion work back together again, and we're all ready to go. So the next stage is to retime the engine and get it running on compressed air again. Now the first time round that I did this, I didn't have my YouTube channel, and I actually showed it on Facebook. I'm on several of the Facebook groups. So I thought perhaps I might go through it here on how I go about timing an engine with Volshirt's valve gear. The first thing we need to do is find the front and back dead centres of the cranks as accurately as we possibly can. So here's a photograph of how I did it originally, and you'll see I have a dial indicator here. I've added this brass extension piece on it, and I'm measuring between I've mounted it on the motion brackets here, and I'm measuring just the back of the drop arm of the crosshead. And what you do is you move the crosshead as far forward as you possibly can until you see this needle stop moving. This then needs to be marked on the wheel somehow, and what I do is I'll have a reference point of some kind. In this case here, there's a spare hole in the frames which I put a bush in, and I've punched a centre hole mark there. Then I've got these large calipers, extended them to their maximum length. Place one point there, which is the reference point, and then I can go and mark the lines. Now when you do this, what actually happens is you've got a little bit of movement in this crank up and down, because remember, you're measuring in thousandths of an inch very, very accurately, and there's a little bit of play in the bearings. Now the bearings are still tight. You can see this is not moving in any way, but the bearings actually need to be slightly bigger than the return cranks. Sorry, not the return cranks, the pins. Otherwise the chassis can't flex, and if it can't flex when you're going along the track, it's going to lock up on you. So you have to take that into consideration. So you'll see there's actually 3 marks on here, and one was when I went to the front dead center, and I watched the needle of the dial indicator, and when I saw it just start to move, I pulled it back a little bit and made the mark. And that might have been up here somewhere, and then I slowly turned the wheel down a bit till I saw the needle stop moving, and I was able to mark the second mark here, split the difference between the two, and that gives you the actual position for the front dead center or the back dead center. In this case here, the crank pin's at the back of the wheel, so we're looking at back dead center. We now move that 180 degrees and repeat the process again to get the front dead center, and you can see down here where I've marked it. So once we've done that, what we need to do then is establish what the angle of this return crank is going to be. Now when I build frames for engines like this, I always use the top edge of the main frame as your reference point, and everything else is built up along that line. Now these frames were laser cut, so I now know that the rear buffer beam is exactly at 90 degrees to that top. So what that means then is I can use this engineer's square and this setup here to get this face exactly parallel with this face up here, and with the crank pin set exactly on back dead center, I know that this edge is parallel with the center line of that motion work going right through the center of the piston rod and through the center of the cylinders. Because I've got the motion work sitting at back dead center, it's a little hard to see, but on Volshirt's valve gear, this here is actually part of a right angle triangle. So you've got a right angle triangle. So from that you can work out what this angle needs to be to give you the correct throw of the piston valve. And from that angle I can make up this jig. It's made in 2 halves, so I can flip it over when I go do the other side. But you can see all I need to do is line up the return crank with that angle, lock it in place, and now I have this in the correct position. The next thing you do on Volshirt's valve gear is you need to get the piston valves to travel equally back and forth over the ports. So the way you do that is I made up this bar you can see in here, this little brass bar, and that accurately locates the die block in the exact center here of the curved link. So I know that that is exactly on the center line, and now all I have to do is pull these covers plugs out and measure where the piston valve is and set that up accurately. So now what I've done is I've removed the timing plugs off the cylinders, and it's very difficult for the camera to pick it up, but I'll put this magnifying glass in here and then shine a light, and it's a bit hard to see, but what you're looking at is the edge of the end of the piston valve. It's on the right hand side, and to the left the darker area is actually the hole or the gap where the steam actually flows. So the next step is to measure that gap and see where the end of the piston valve is compared to the end of the hole here, and I can actually put a drill down there and very carefully measure the gap like so. So then I record what that gap is. I then turn the wheels 180 degrees so the piston is moved to the front, and that's front dead center, and then I can put the drill in the other end, in the other hole I should say, and repeat the process and see if the gap is the same, and if it's not, then you move the piston valve along the spindle here until you get it right, and you keep moving between front dead center and back dead center, and front bed back dead center and back bed dead center, until you've got this valve moving equally across this distance, and the drill, the same size drill, can be used in both ends. Once you've done that, the valves are set. So I can put the timing plugs back in now. I can go back to the other side and I'll set the other side up the way I've just shown you, and then we'll run it on air. To explain a little bit better what you've just seen, I've pulled out my sketches of when I designed this all up, and this is the piston valve liner that sits in the top of the cylinder. This shape here is the actual piston valve itself. You can see it here in this drawing. The timing plugs are sitting here, and the camera was looking down here. So this is the steam port, and you can see the back of the piston valve is actually sitting in line with the steam port. But when you turn the wheels to front dead center or back dead center, this valve will move along a little bit, so that edge moves across the port a little bit, and then this is where I was putting the drill bit down to measure the gap. So front dead center, I'd measure that one, turn the wheels 180 degrees for back dead center. The edge of that valve will move back slightly, and I can put the drill down there and check the gap. And as long as the gaps are even, that valve is going to move across these port faces correctly. And the design of the piston valve and the design of the valve gear ensures you have your lead steam. This engine's actually inside ignition, so the steam actually comes into this area here, and it is this edge here moving across that port that determines the steam flow into the pistons and pushing the pistons along. And then these bits here, that's the exhaust. So once the steam has gone in, done its work, it comes back out again, flows at the back and into here, and exhausts out through the pipe work. Here's some more of my notes here. You would have noticed in the last drawings of the piston valve there I mentioned Doug Houston, and what I did when I was building the motion work and setting it all up, I followed his notes from the Model Engineer magazine, but the actual design of it I used Don Ashton's valve gear program. These are the notes that have come from that. That gives me all the dimensions that I need for everything. So all I basically have to do is tell the program what the bore and stroke is, where the position of the curve link sits, also where the rear wheels are sitting compared to the centre line of the cylinders, and a few other dimensions. So there's quite a bit of data you have to put in, as you can see, but once you put it all in, it calculates the optimum lengths of things and positions of things and makes designing the valve gear so much easier. I'm going to leave it there for part 6 of building the Garratt, explaining how valve gear works. It's quite intricate, and I'm trying to take my time to make it easy for you guys to understand. Hopefully you do. So we've run out of time. So in part 7 I'll give you a quick demo of the engine unit running under air, and we'll continue working on the Garratt from there. See you next time.